pick up where we left off in 4.4, which was the fundamental theorem of calculus. From there we transitioned into two important ideas. One is the mean value theorem for integrals. We've done the mean value theorem for derivatives already, which said what, Matt? What's the buzz phrase for MVT for derivatives?
What?
Thank you, Matt.
You're welcome.
You'll now be referred to as Matt number 1. She'll be Matt number 2.
I plugged it in.
Matt number 3.
Matt number 3. Well, you should really be Matt number 2. You'll be Matt number 3. Slope from calculus equals slope from algebra. Mean value theorem for integrals is something completely different. However, it has a name, so it's very important.
This is
4.4. Second half of 4.4. All right, so we're going to start with this idea. We've got a glass that's filled with some ice, some crushed ice. It's a little bit easier to visualize. And you see the surface of that ice is all uneven. I think it says uneven and scraggly. Not sure if that's how you spell scraggly. I did the best I could. Might be EY. I'm not 100% sure. Do we all agree that as that ice melts, it will eventually level out?
Yeah.
Do you not agree with that? Okay, you don't.
Stop with this double negative stuff. I agree with it.
You agree with it. You don't not agree with it.
Yeah.
Good. Okay. In other words, we'd have a glass of water. That concept is what we're going to use for the mean value theorem. The mean value theorem for integrals is sometimes referred to as the meltdown theorem because of this example. As that function, which we're going to use the ice to represent the function, melts down, it eventually approaches this level surface. That level surface is the mean value. So we get something like this. So imagine the red is the ice in the glass. And the glass is the blue segments that are vertical. Okay, so I got some ice outside the glass, just ignore that. As that function melts down, it will eventually reach this level where the entire function has that value. That level is over on the left called f of z. The point where that function hits that meltdown level is referred to as z. So you get that z to f of z relationship again. Okay, so the function is our ice, and a to b represents our glass. So we're taking only a part of the entire function. In other words, we're restricting it. And again, f of z is called the average value of the function, or the meltdown level. Technical term is the average value. The x value where that happens is called, as I said already, is referred to as z, which is right there. Notice in this function, however, I do have another z value over there on the left. I just didn't highlight it. Okay, you see where f of z hits the function. That is possible to have more than one z value, depending on how complicated the function is. The important thing to notice is that because it's an average value, we should have this relationship. If I take the area of the stuff above the function, it should equal the area below. Okay, so if that is truly the average value, then the blue region should match the green region. So that when it melts down, we hit that level point. We're going to be calculating where that happens. We're going to be calculating two things. We're going to be calculating the y value, our average value. We're also going to be calculating the spots where that happens. And again, there would be another one over here. I just didn't highlight it. So we'd call that Z1 and Z2. Okay, that's the concept. Now, how to find them? I got a nice little formula for you. Can I go? We're solid? Okay, there's the formula.
We're actually liquid.
I'm sorry?
We're liquid is melt down.
Don't ever do that.
Well, I had to do it because Aton's not here.
I
had to take his
understand.
spot.
You figured that would have come out of
Yeah, I figured you would say it.
Good. They'll appreciate you filling in for
Yeah.
them.
That's very tactics.
Not that smart.
Aton is so smart. A little Aton.
Can you go back?
Can you see that bounce, Mike?
No.
Oh, slide wise? Yeah, there you go. Hold on, relax. I'll go back to the back. No, I'll go forward, back. No, I'll go back to the forward.
Yeah.
Back to the future.
Back to the front.
Yes. Did you get it?
No. Okay.
Now you good?
Yeah.
Okay, there you go.
When I keep.
Was that a max or is that an aton?
It's both.
Both. A maton. Or an atax.
Aton.
Apex sounds like it should be an animal. It sounds like Apex.
You went on safari and you were attacked by an atax?
No, it sounds like it would be like something related to a gazelle.
To a what?
A gazelle or an antelope.
No.
There is an animal that sounds similar to that.
Yes, maybe I'll think of that.
Similar to Atex?
Yeah.
So Ajax
It's
is
kind
the
of a-
city of Ontario.
That's true.
Yeah.
Also the god of war.
It just reminded me of
Ajax?
Evox
Yeah.
from like the Hunger Games. That's what I don't know why it sounds
Avox? I'm not real familiar with the Hunger Games. I'm
Oh,
sorry.
it's like
That was Ares.
wouldn't it-
I missed that vote.
Those Canada's ops.
I missed it.
I'm sorry.
Shut that mouth.
Sorry. All right, I'll have them read before we come back from break,
Okay, good.
just so you're not so upset.
I'll quit this.
Okay, great.
Ajax also conquered all.
Oh, really?
Uh-huh.
Isn't Ajax a soap?
It's also.
It is a soap also. yeah.
That conquers.
Yeah, that conquers dirt.
Yeah, you know why? Because it fights grease.
Okay, so how do we do that? I took this and changed the terminology a little bit. So if we go back to this guy, we're using f of z, but I rewrote it a little bit differently. I just took the b minus a and divided it to the other thing and changed the name. Now, why did I do that? Just to confuse you? No. It's because certain sources use different notation. Some sources will use f of z, some will use f sub av, or the average value. Just so you get used to them and notice the thing, since it's in a colored rectangle, it's pretty important. But f of z and f of av are the same thing. Okay, so we're going to plug and chug and do some calculations next.
Wait,
What? There's nothing new on that slide, except f of z equals f of av. Same picture, same function, same everything.
Why is that one over b minus a?
I just took this one and divided both sides by b minus a. Okay, so here's the first function. X cubed will deal with something we can work with. Easy to find the antiderivative of. And I'm going to start by calculating the value of that integral, because I'm going to need that somewhere in the calculation. So the area under the curve from 0 to 4 of x cubed is equal to that value of 64. We've done that one a number of times now. Now I want to find the average value of the function. In other words, if I take that x cubed function and I melt it down from 0 to 4, at what level will our glass of water be? So I need a 1 over b minus a. That's pretty easy. Getting there, hold on. There we go, right there. So the average value, in other words, the y value, or the height of that rectangle when the function melts down, will be at 16. 1 over b minus a times the integral from 0 to 4 of the function gives us 16. If I go backwards, I want to know what x value will that y value give me. We usually go from the x value to the y value. In this case, we're going to go from the y value backwards to the x value. How do I find the x value?
Plug it back in. No, that would be the
Watch it.
Would you plug 16
Oh, no, 16 equals
That was the question I was gonna ask you. Where would you plug it in, y or x?
Y.
Y, correct. Set the function equal to 16 because that's a y value and solve for x, and you get the cubic root of 16, which is 2.519. And since we knew f of z, or f of average value, we didn't need to do all that calculation again, I just threw it up there again. Take that value for the y, set it equal to the original function.
Why don't you turn to his
What's up?
matches?
All right, we good?
No,
How do you,
How about now?
no,
how do you?
no, I don't get it.
I'll draw you a picture. Okay, the cubic function looks something like that, you know, there's another bit, but we're just gonna deal from 0 to 4, so I come over here to 4. Okay, there's my glass, so I'm gonna go from 0 to 4. I have to find the level so that when I draw a line through here, the area above the line will match the area below the line. Okay, and I know this point is at 4 comma 64, because 4 cubed is 64. And so I want to figure out where I can draw a horizontal line through here so the stuff below matches the stuff above, so that when it melts, I reach that level. Okay, so if you imagine this function made out of ice, as it melts, it's going to level out, and we want to know where that happens, and it happens down about here. It actually happens 1/4 of the way up. Okay? This is f of AV or f of z. F of z or f of AV. And we found that by solving the original function for f of z. The second part, actually working backwards, is I want to know what x value, where does that happen? So if I come back here, go back this way, hit the function and go down, that's where my z value is. And I found that by setting x cubed equal to the y value of 16.
How did you know it was 16?
By using the formula a couple slides ago. The 1 over b minus a times the integral from 0 to 4 of the function.
Yeah, there's a lot of
Okay?
scrimmages.
All right. Second fundamental theorem of calculus. This is what we talked a little bit about on Friday. I gave you some hints about it. We're going to look at functions that have different variables. So we'll start with an f of t, but then we'll start incorporating x's into it. So we get this. And again, I'll go through this quickly because we talked about this a little bit. When we've done our definite integrals already over here on the left, I've taken some function f of x, and I've found the antiderivative of f of x, and then plugged in b and plugged in a and subtracted them. That's the first fundamental theorem of calculus. Nothing fancy there. We're going to change it for the second one by looking at this scenario. Instead of f of x, I have f of t. Does that matter? Absolutely not. It's just some function. It doesn't have to be f of t. It could be f of q. It could be f of anything. But now what I'm going to do is I'm going to go from a constant to some other variable. So the common terminology here is we go from t to x. You could go from x to t, which is I think what I did on Friday. You could go from k to l. You could go from q to p. It doesn't matter. We're taking one function in terms of in terms of a variable and changing it to a different variable. And we did that calculation on Friday. Now, what happens when we do that is we end up with this, and I want to evaluate that function. So we'll go through the calculation again for cosine. What's the antiderivative of cosine? Sine. Then what? No plus c. It's a definite integral.
Sine x minus sine constant.
Good. And our constant in this case is a. Okay, so we get that. Sine of x minus sine of a. That's just a definite integral. Doesn't matter what the function is, you take the antiderivative, plug in the top value, plug in the bottom value, and we get that. Okay, nothing fancy there. The second fundamental theorem of calculus, however, then takes that idea and complicates it a little bit. It complicates it by taking the derivative. Everybody caught up? Okay? So now, I want to take the derivative of that. Let's go back to this slide. What happens when I take the derivative of this function? What's a derivative of sine? Negative cosine. What's the derivative of sine of A?
0.
0.
How do you know A is a constant and X is not?
Because it's just A and B are always constants. X is always a variable.
Unless it says
Correct. So notice what happened. We ended up back where we started. The only thing that changed, well, you tell me, what changed?
The variable.
Yeah, the variable changed. The t magically became x's. This whole process that we went through is the theory as to why it changes. You take the derivative, or sorry, the antiderivative of the function, you plug in your limits of integration, you get a function. You take the derivative of that function and you end up back where we started. The only difference is that the variables changed. I will commonly refer to this as a variable change problem. Just get rid of all the t's, put in x's, and you're good to go. Question?
I don't understand what you did.
Do you understand what this is? I did that in the previous slide. It's right here.
Yeah.
Okay? So then all I do is take the derivative of that. Derivative of the sine of x is cosine of x. The derivative of negative sine of A is 0 because it's constant.
Wait, A is a constant or
A is a constant. A is always a constant.
so? Okay.
Then, but X is not.
X is not. No, x is a variable. X and t are variables. A and b are constants.
It's just too
It is a little confusing, yes.
I kind of missed the
Yeah, the derivative is the important part
So
there.
like, big you do like the derivative of cosine of
Would we add d of x to the end of cosine x?
No. You cannot have a d of x without an integral symbol.
If you're doing, what, would you ever have that or
No. And if you have an integral symbol, you have to have a d of something. Those two go hand in hand, like peanut butter and jelly. I'm sorry? Hi.
Hi, Ryan?
Brian? Keep your guard up. She comes in strong with the right. Yeah. Okay, so do you want another example?
Yes.
Okay, let's do this. Let me get a blank screen here. Let me make sure I don't have another example here coming up. Nope, not yet. Okay, let's do another example here. What happens if I want to take the derivative of the integral from 2 to x of t cubed dt? I'm going to solve this problem two ways. I'm going to solve it the hard way using the theorem, and then I'm going to solve it the practical way, which is the way you're going to do it from this point on. Which one should I do first? The confusing way?
Yes.
Okay, so the confusing way is I'm going to do this stuff first, and then take the derivative of what I'm done with. Okay? What's the antiderivative of t cubed?
1/4.
So I'm going to end up taking the derivative of 1/4 t to the 4th evaluated from x to 2. And let's clean things up a little bit, put brackets around that. Which becomes 1/4 x to the 4th minus 2 to the 4th. 2, 4, 8, 16, so 4. And then I'm going to take all of that stuff and take the derivative. What's the derivative of 1/4 x to the 4th?
X cubed.
X cubed. What's the derivative of negative 4?
0.
Now, where'd you get the negative one?
You
Plugged in 2 into that. Okay. Question?
Can I go to that?
Yes.
Is that the final answer?
That's my final answer.
Oh.
Now, what you're going to do, practically speaking, you're not going to go through this hassle because a lot of times when you're asked a question about the second fundamental theorem of calculus, you're going to have a function that's so nasty you're not going to be able to take the antiderivative of it. What you're going to have to realize is I'm taking a derivative of a definite integral with a variable, and you're just going to look at this and say, okay, change all the t's to x's, x cubed, done. It's that simple. I'll give you one more example.
Mr. H.
Yes?
On the test or a quiz, is it okay if we just substitute all
Yeah, that's what you're supposed to do.
Alright,
What's that equal to?
x squared square root x squared minus 7x plus 2.
Done.
That's all the work you need to
That's
show.
all you gotta do.
It's a miracle.
But isn't the 2 a constant? You don't get rid of that?
What 2?
The plus 2?
No. Because when you take the antiderivative, you get something with a variable on it. When you take the derivative again, you get back 10.
So is it whenever you take the integral?
Not always, only when your upper limit is a variable. Okay. Dan brings up a good question. Let me ask you another question then to go along with it. What's this?
Zero.
Correct. 0. Why?
You're taking derivatives constant.
Yeah. This business here will give you a numerical value. It's the area under the curve of this nasty function. Take the derivative of a number, you get 0. Okay. So this will happen when you're taking a derivative of an integral from a number to a constant. And notice in these problems, this number does not matter. Positive, negative, big or small, rational, irrational, it could be from pi to x, it doesn't matter.
If we get a question where we're taking the derivative of an integral, the variable's on the bottom. And then
Flip
we
it
have the
over and put a
constant,
minus sign in front of it.
flip
Yep.
Why is that one 0?
Because this is a constant. It's a
You
number.
just said it was never a constant.
This is, yes,
Why?
because it's the area under the curve.
There's no variable.
It's
There's
the
no
definition of our
variable.
definite integral.
That's
Okay.
because x isn't on the, like, the s thing.
Yes.
Will it always be 0?
Will what always be 0?
It's like,
A definite integral with numerical limits of integration? Always. Okay? It would be nice if we were done with that, yes? Yeah, we're not yet.
Oh,
Because there's one other little snafu that gets thrown in here, and that is, what if the variable up on top isn't just x? What if it's another function? What if, for instance, I put an x squared up on top there? It's easy. The only thing you need to remember when you do this, it's a variable replacement. So all the variables, all the t's become x cubed or x squareds. The biggest thing to remember is that you have to chain on the derivative of that thing. And we can go through the process of why that comes about, but you don't really care about that. We would do the same thing we did when it was just plain old x. We'd take the antiderivative of it, plug in x squared, plug in 7, take the derivative of it, everything disappears. But when you take the derivative, you'd have to chain on the derivative of that x squared that you subbed in. Okay? So this is still a variable replacement. It's just you have to remember to chain on this. The easiest way to remember this is if you're taking the derivative of a definite integral with a function up on top, just chain it on. Because even if it's just x, what happens when you chain on x?
1.
Yeah, you're multiplying by 1. And also notice it's just not a matter of changing t's to x's. It's a matter of taking this x squared and plugging it in for all the t's. I don't have another t there, so I'm just going to have that go over there. Okay, Just ignore that. This doesn't, this is not here. Pretend it's not there, okay? So just that, that's why that became x to the 4th. Okay, that's better. Got it? Not one of my better moments. We're all done. So that takes us up to day 61. You're actually, I think you're gonna be on day 60, which is the 3rd day of 4-4. So you did 32 and 40, 32 and 44, 42?
34 and
42.
34 and 42 on Friday. So finish up that 3rd day of day 60.
Can you go over 34? on
Sure.
Friday?
Yeah, let me stop this.
Wait, did you go back really fast?
Wait,
Could you repeat the homework again? What did you just say?
The 3rd day,
Finish with the page that three.
may I, Molly?
Yeah.
Thank you.
Day 62.
Day 62.
Okay, but we
Okay.
already did the first stuff.
But you did the first 2, so don't do them again.
Awesome.
Okay?
Can we just do them on the same sheet of paper?
That'd be awesome.